Stripping down science. The Naked Scientists.
Hello, it's Sunday the 4th of September and welcome to The Naked Scientists. I'm Chris Smith and also here this week are Dave Anzo. Hello, Dave.
Hi there.
And also Emma Stoy, who is our MRC, Medical Research Council, Naked Scientists intern this summer. She's joining us for 6 weeks to learn how to do what we do. Hi, Emma.
Hi.
Now, together with these guys, this week we're answering your questions, including these that have already come in. What happens to liquids on an orbiting spaceship or out in space in microgravity? Also, how do some fish, like salmon, survive in both fresh and in salty water? And what causes pins and needles? And is it harmful?
And in this week's Science News, you are what you eat. Scientists have discovered that probiotic foods don't just improve digestion, they also alter your brain chemistry.
And this week I've come equipped with a laser for this week's Kitchen Science, and I'll be exploring the microscopic life living in dirty water.
And he really is waving a laser around in the studio. I don't know what he's going to do with it. We'll find out later. If you'd like to get in touch, though, we love hearing from you, and you can tweet at Naked Scientists. You can also write on our Facebook page. We've made it very easy for you to find it. You go to nakedscientists.com/Facebook, or you can, of course, drop us an email to chris@thenakedscientists.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
And this is The Naked Scientists with Chris Smith, with Dave Ansell and with Emma Stoy. And we're going straight to the heart of the matter with a story about modelling drugs in hearts that don't even exist, Emma.
Scientists in the US have created a completely computer-generated model of the human heart that can successfully predict the effects of drugs used to treat arrhythmia. Now, arrhythmia, or irregular heartbeat, results from abnormal electrical activity in the heart, and the drugs that used to treat it act on the heart cell membrane channels to alter the flow of charged molecules called ions, which are what cause the electrical signals in the first place. And worryingly, if they're used at the wrong concentrations, these drugs actually make arrhythmia worse or can even lead to sudden cardiac death in patients. So it's really important to test them thoroughly to determine the doses at which they're actually safe to use. Now, traditional methods of testing, which involve using animal hearts or looking at human clinical data, are incredibly inefficient. So researchers at the University of California have come up with a completely different approach, a computerised model of the human heart. Now, in the model, mathematical equations represent the opening and closing of ion channels in individual cell membranes. Other equations connect these events among single cells in order to simulate the whole heart. So you can then sort of mathematically feed drugs into this framework and test their effects. So they tested the effects of two widely used antiarrhythmic drugs, that's lidocaine and flecainide, at different concentrations to determine sort of what concentrations and conditions they worked, where they made the arrhythmia worse. And actually, really remarkably, the model's predictions were validated both by looking at clinical data and when they carried out similar tests on a rabbit's heart. And this is really, really exciting because this approach could potentially speed up the whole drug development process and help treatments get to patients so much faster. Now, I spoke to one of the authors of the research, Colleen Clancy, who said that they're now planning to extend this framework to cover more drugs and also investigating ways of scaling it up, and then it could be used to screen drugs. They're actually still under development. That was reported this week in Science Translational Medicine.
Something that suddenly strikes me as could also be useful with this sort of thing is if you have a model of a heart, you could also kind of damage it. So if you had someone in front of you with some problem, you could then put that into the model and then see what giving the drugs would do to them.
Yeah, absolutely. And this is the sort of thing they're looking on. They're looking at more drugs. They're looking at different heart conditions. They're even looking to see if this approach could be extended to other organs. I happen to know the same lab are looking at modelling the hippocampus in the brain to look at treatments for epilepsy and kind of because it can really sort of speed up the whole approach.
It's amazing to think that you can do on a computer what would have taken, as you say, lots of studies in both animals and in humans in the past. Well, also in the news this week, the question of resistance to antibiotics is barely ever out of the headlines. We see news stories about this bacterium becoming resistant to this commonly used antibiotic and that one all the time. And so you might think, and many people do think, that antibiotic resistance is a fairly recent phenomenon. Actually, that's definitely not true, and there's a wonderful paper in the journal Nature this week to prove it. Vanessa da Costa and her colleagues went to a place called Dawson City, this is in Yukon, and they drilled down 6 metres underground, and they extracted core sediments from this permafrost that they were drilling into, and they used carbon dating to prove that it was at least 30,000 years old. And then they started amplifying or analysing the DNA which was in those old samples. They could clone out DNA from old trees, they cloned DNA from bison, even mammoths. And so then they started looking at bacteria, and specifically they were looking at genes from bacteria which we know are linked to resistance to antibiotics. And out of this 30,000-year-old sediment came the genes which enable bacteria to break down vancomycin, one of our last-ditch antibiotics we're using today. It kills MRSA, for example. Also, TET-M, that's a gene which breaks down the tetracycline family of antibiotics. They found that too. And they also found beta-lactamases, drugs that break down penicillin. And to prove that these genes they were finding actually worked, they cloned the vancomycin resistance gene into E. coli, a culture growing in the laboratory, and they were able to demonstrate that this ancient 30,000-year-old gene sequence had activity that would be capable of breaking down this antibiotic today. And they also compared the crystal structure of the antibiotic resistance protein with the one that's used by bacteria today, and they were almost a direct match. There were a few minor changes, but they were almost spot on. So what they say in their paper is, and I'll quote from their Nature article, this work firmly establishes that antibiotic resistance genes predate our use of antibiotics, and it offers the first direct evidence that antibiotic resistance is an ancient, naturally occurring phenomenon that is very widespread in the environment. And the reason that this is happening is because at the end of the day, the drugs that we use as antibiotics, we just nick the idea from nature in the first place.
So is this actually quite hopeful? Because if we could come up with an antibiotic which nature hadn't thought of, then nature wouldn't already have the resistant genes there, so it'd take much longer to develop resistance to it.
It's a good thought, Dave, but unfortunately nature has something like 3 billion years of head start over us, so I think it's a tall order, unfortunately.
Now, on a completely different subject, tiny gold rods may give us unprecedented control over light. Light is vitally important, not only in our everyday lives to avoid bumping into things, but to our technology, ranging from transmitting our phone calls and internet down optic fibres to making computer chips where you actually use a process called photolithography and you make the patterns using light. So any improvement in our control of light should help us in all sorts of different ways. Now, light will travel at right angles to its wavefront. A wavefront is, if you imagine drawing a line on the top of a wave, that's its wavefront. The wave will always travel at right angles to that.
It's a bit like if you're at the seaside, the wavefront would be the waves coming in towards the beach.
Yeah, the top of the wave, so they always travel at right angles to their line at the top. So you can now control this. Normally you can do this with a mirror or by using a material which slows light down like glass, allowing you to bend the wavefronts, and therefore you can focus light using lenses or prisms. But this is very limited in what you can do. Federico Capasso and colleagues have managed a much finer control. They've managed to make tiny gold rods, or bent gold rods, and pattern them onto a silicon wafer. These are smaller than the wavelength of light. And when you shine light on them, you could get electric currents induced, so they slosh up backwards and forwards. And depending on their exact shape, it depends on the natural frequency they want to vibrate at, the resonant frequency.
Oh, so do they, when they vibrate like that, do they give the light back out again? Because their current is moving up and down, therefore you've got a moving electric field, so you get a moving magnetic field and you regenerate light.
That's right. I'm not sure whether they actually technically get absorbed and re-emitted, but they certainly interact with it very, very strongly. And by tuning the shape of them, you can change the amount they slow light down. They've managed to make a thing which works like a prism but is completely flat. So they've basically had lots of different delays across a piece of silicon. They shine light through it. And at one side it's delayed a lot, a bit like a thick piece of glass. On the other side it's not delayed hardly at all. So the light bends and it acts like a prism.
Wow, so that's like a flat lens basically.
And then, in fact, yes, they haven't built one yet, but you could in theory build a completely flat lens. Another thing they've done is they've kind of arranged it in a circle. So as you go round a circle, the amount of delay changes. So you shine flat light onto it, and then the light coming off actually sort of spirals out.
Very nice, but why would you want spiralling light?
It's used in various things. You can interact with molecules differently because it's spinning light, and if it hits a molecule, it would make it spin. It can also be used in things called optical tweezers because you have a little dark patch in the middle with really bright light around the outside, and that can trap atoms, molecules, or even cells.
You push things into the sort of black hole, quite literally in the middle.
Stuck in this black hole, and you can move them around. So that's kind of useful, but I think it's more a kind of proof of concept. And in the longer run, it means you can essentially shape this wavefront almost any way you like. And so you can actually produce patterns of light smaller than a wavelength if they get it all right.
is the tricky part, that it's really difficult to make these things to the kind of detail and resolution that you would need to shape the light in that way. I mean, that must be the hardest bit about doing this.
I think they're probably using electron beam lithography to do that, because an electron's wavelength is much smaller than the wavelength of light. You can make it very, very small, but obviously making billions of them would be very expensive unless you can somehow get them to self-assemble. But yes, we'll see how these technology develops.
Brilliant. Thank you, Dave. Well, also in the news this week, researchers from University College Cork and McMaster University in Canada have found that the so-called good bacteria, also known as probiotics, don't just affect the digestive tract, they can also affect mood and potentially have an impact on stress and depression. And joining us now to discuss how they've done this work and what they've discovered is Professor Paul Forsyth, and he's at McMaster. Hello, Paul.
Hi there.
So, first of all, what was the question you started out by asking when you were doing this work?
Well, over recent years, there's been a real increase in our understanding of the importance of the normal bacteria in the intestine, the gut microbiota, and how it influences a whole range of physiological systems. And what was particularly interesting in us was evidence emerging that these bacteria could influence the brain and brain development. And so we had been investigating the particular bacteria that we used in this study for some time, and we had demonstrated it could actually alter the activity of nerve cells in the intestine of mice. But what was really interesting, it could actually reduce the perception of pain signals coming from the gut. And we took this as a good indication that it was modifying the communication between the gut and the brain, and we wanted to explore this further and to see if we could actually detect changes in brain neurochemistry and subsequently whether these changes in brain neurochemistry might alter the behavior of these animals.
So the bacteria that go into the intestine in some way change the chemical environment in the tissue of the intestine, which in turn changes the activity of the nerve cells in the intestine, and you're saying that can be then propagated, or at least you speculated that could be propagated up to the brain and in turn alter neurochemistry in the central nervous system.
That's it. And actually what we demonstrated was that the vagus nerve, which has already been shown to be an important communication system between the gut and the brain, was critical to mediating the signals from the bacteria to the brain. So if there was no signaling going along the vagus nerve, we didn't see the changes in the brain when we fed the bacteria.
So talk us through the experiment. You did this in mice?
We did, yes. So we fed mice with a particular strain of Lactobacillus rhamnosus, and we fed them for 28 days. We then conducted a number of behavioral tests, specifically looking for things like anxiety, and then we looked at the brains of these animals. We initially focused on the GABAergic system in the brain, and so we looked at receptors for the neurotransmitter GABA, and we saw changes in those receptors in the brain.
Which bits of the brain did you look at, and which bits of the brain showed those changes? More critically, were they the bits of the brain that would be consistent with the observed behavioural effects you saw in mood, stress, depression, that kind of thing?
We did. So we focused on the hippocampus and the amygdala. They have both been related to changes in things like depression and anxiety. The changes we saw were consistent with the changes we were getting in behaviour, so a reduction in anxiety-like behaviour.
So how do you know that the link in the chain was gut, nervous system, i.e. vagus nerve, brain? How did you rule out the fact that the animals weren't just feeling better and healthier because they had these bacteria in their guts and that was impacting on their behaviour?
What we actually did is we severed the vagal nerve. So there was now no signaling going from the intestine to the brain through the vagus nerve, and we lost the behavioural effects and lost the changes in the brain chemistry, indicating that the signal to the vagus was critical. And animals that were fed just broth without the bacteria, they had no changes in their behaviour at all.
So that's pretty encouraging, isn't it? It shows that there is definitely some kind of connection going on via that vagus nerve between the gut and the brain. You only looked at one nerve transmitter chemical. There are many others in the brain. Are you now going to go ahead and say, look at some of the other, what we know are mood-related nerve transmitter chemicals and see if they also get changed?
Exactly. I mean, we focused just on the GABAergic system in this study, but as you say, there was a whole range of neurotransmitters involved. We don't know the extent of the changes caused by feeding this bacteria, and that's definitely something we're actually looking at the moment.
And what about in humans? Is there similar clinical data that it has the same effect when humans consume these bacteria in these yogurt drinks and things?
The studies in humans are very limited and tend to be looking at reducing the anxiety effects or chronic fatigue and things like that, but the studies have been quite small and the data is limited, so we don't really know what the effect of these bacteria would be on humans, and that's obviously something that we want to look at.
And of course, related to that is what actually are the bacteria doing to have that effect in the gut itself, and is there some other way of mimicking the effect, i.e. if you ate something different, would that have the same sort of impact on the gut as these bacteria do?
Sure, exactly. I mean, looking at the bacteria itself, so what are the characteristics of that bacteria that allow it to mediate these signals? Is it something to do with the cell wall of the bacteria, or is it a product that bacteria produces? And then how it transmits this signal to the vagus nerve. Does this involve other cells in the gut, immune cells perhaps, or is it a direct effect on the nervous system? And then we're also interested in looking at what's the nature and the change of the signal along the vagus nerve that mediates these anxiolytic-like effects. I mean, it's interesting to note that electrical stimulation of the vagus is actually approved treatment for depression, so it's quite encouraging that it seems our bacteria is acting on that same signalling pathway.
All right, well, we must leave it there. Thank you, Paul. I think that's very good proof that you are genuinely what you eat. That was Paul Forsyth. He's the Assistant Professor in the Department of Medicine at McMaster University, and he published that study he was discussing this week in the journal PNAS. Now, looking at what else has been making scientific headlines around the world this week, here is Meera Senthilingam with a new feature that we're kicking off this week, and it's called The Naked Scientist Newsflash.
Scientists studying how forests develop have discovered a new source of nitrogen that plants and trees can tap into, helping to boost their growth and so remove more carbon dioxide from the atmosphere. By analysing samples of soils from coniferous forests in Northern California, a team at the University of California, Davis, found that the underlying bedrock leaches nitrogen-containing chemicals into the soil, nourishing the plants and trees growing above. This source of nitrogen was previously unknown, according to Professor Benjamin Holton, who was part of the study.
It was thought for a long time that the way nitrogen comes into our environment is from the atmosphere only, and especially by way of a couple of interactions, one involving bacteria known as rhizobium, and in addition, it can come in rainwater. But it turns out that there's a tremendous amount of nitrogen that's in rock material. This is a kind of a new discovery that nitrogen actually is in the rock material, and it's also available to forests and other types of plant ecosystems.
This new source of nitrogen is released by the rocks as they erode, according to the group's paper published in Nature this week. More nitrogen, which is an essential ingredient for the formation of proteins and DNA, means that plants and trees grow faster, storing more carbon dioxide from the atmosphere as a result. The findings could therefore be used, say the scientists, to identify fertile areas in which to site forests intended to function as carbon offset schemes in the future. Using mobile phones to track how people move about in emergencies has enabled scientists to develop better ways to target aid where it's most needed. Publishing in the journal PLOS Medicine, Linus Bengtsson and colleagues from the Karolinska Institute in Sweden used mobile phone signals to follow the movements of more than 1.9 million people affected by the 2010 Haiti earthquake and ensuing cholera outbreak to predict with very high accuracy where people will go, in what sorts of numbers and over what time period following an emergency.
What characterizes a disaster is often total chaos, and it's very, very difficult to understand where people are. Since we know which tower each mobile phone used, we could sort of follow each phone as it travels across the country. We could see that approximately 600,000 people left Port-au-Prince 19 days after the earthquake. So our hope is that this will contribute to making aid delivery much more efficient.
A DNA-based circuit that trips and kills cancerous cells has been engineered by scientists at the Swiss Institute of Technology and MIT. Described this week in the journal Science, the new system looks for specific microRNA molecules that are known to be present at higher than normal levels within cancer cells. Once a threshold level of the microRNAs is detected, a DNA domino effect is triggered, causing the cell to self-destruct by a process called apoptosis. Although the team have yet to solve the problem of how to achieve safe and large-scale delivery of these cancer-preventing trip switches into a patient's cells, lead scientist Jakov Benenson believes the work could be a strong contender in the search for new, more specific cancer therapies.
If we think about what would be the ideal anti-cancer therapy, so it has to be something that look at each cell and determine whether it should be destroyed or should be left alone. We don't have any good ways right now to do so. So I think our study shows how to look inside the cell and detect what's going on with the cell with high precision based on all this integration of multiple cancer signals and markers.
And finally this week, scientists at the University of Leicester have developed a Star Trek-style sick bay that can non-invasively diagnose a variety of illnesses all at once. Co-inventor Professor Paul Monks explains how the technology can see, smell and feel disease.
The first uses imaging technology, which has really been developed for use on the Mars rovers, to look at the colour of people's skin, for instance, to see whether we can pick up disease from that. The second suite of technology looks at the composition of people's breath, and from that you can actually tell how well people are. And the third suite of monitors really looks inside the body, but non-invasively, to look at blood flow and how much oxygen is in the blood and muscles and skin at any given time. Put together, it's the first time that you'll get this holistic measure of a patient's well-being.
The whole diagnostic process should take just 15 minutes and will be based at the Accident and Emergency Department at the Leicester Royal Infirmary, which sees 150,000 patients coming through its doors annually. The system is hoped to pick up a range of diseases, including infections, heart disease, skin conditions, respiratory problems and some cancers. Liver disease, asthma and even MRSA are earmarked for the future. So what was once considered to be science fiction looks set to become a reality.
Meera Senthilingam, thank you very much, Meera. And you can follow up on all of the stories that we've covered both in the main news and in Meera's news flash on thenakedscientist.com/news.
Keeping you abreast of the world's best science. The Naked Scientists.
And you're listening to The Naked Scientists with Chris Smith, with Dave Ansell, and this week with Emma Stoy, who's our special guest. She's one of our MRC summer interns. She's working with us over the summer to learn a bit about broadcasting. Isn't she doing an amazing job? Emma, let's see how you handle this one. Oh, and I'll just sneak in here. There's a Twitter message that's come in from @LegalAware. If you want to tweet @NakedScientists, you can send us a message that way. And he says, the gentleman from McMaster, referring to Paul Forsyth, he might well have stumbled on why some people feel very depressed after they get bacterial food poisoning. I guess he might be right, but if they've got very bad bacterial food poisoning, as a recent victim of this myself, I can tell you there's plenty of reasons to feel depressed, though. Emma, here's a lovely one from Jessa Samayo, who says, how do fish survive in both fresh water and in salty water? I guess what she's getting at is this question of fish like salmon that can start off in a freshwater river and they're happy there, and then they go out to sea and they're in a totally different environment. How do they tolerate that?
Right, so that's a really good question. The thing is, wherever a fish is, in order to survive, it needs to keep its blood at a constant salinity or salt level. And that optimum level happens to be much less saline than seawater, but a lot more saline than freshwater. And this ability to kind of regulate this is called osmoregulation. Now, all fish can osmoregulate. So some fish that live in a saltwater environment and only live in a saltwater environment, such as tuna, they drink the very, very salty seawater, so their kidneys are specially adapted to excrete lots of salt, and even their gills can excrete salt in this way so that they keep their blood salinity levels at that optimum. Freshwater fish are the opposite. Their kidneys excrete lots and lots of water, and their gills do also, but they manage to hang on to all the salt to keep their blood at the right salinity. But then you have these odd fish called euryhaline fish. They're like salmon, like eels, like striped bass, and they have to be able to tolerate huge changes in outside salinity, either because of their life cycle, like the salmon, which kind of goes upstream into freshwater to spawn, or if they live in an environment like an estuary where the river meets the sea. And they're actually capable of switching from one kind of osmoregulation to another, which these sort of large regulatory changes are controlled by switches in their brain. But it's worth mentioning they actually still need quite a bit of time to acclimatise to new salinities while these regulatory mechanisms are kind of switching over.
Do you think the fish therefore change their behaviour? So if they're swimming down an estuary, would they just naturally adapt because it takes time to swim all the way down the estuary and the water's going to get more and more salty as they do it? Or do they loiter in a certain area and expose themselves gently to the rising salt so that they don't literally get a bit of a shock when they go from fresh to really salty?
I don't know for sure, but I should imagine that they, as you put it, loiter a bit so they can take the time to switch their system over to the new kind of salinity level.
Terrific. Thank you very much. Emma, if you have a question for us here at The Naked Scientist, we'd love to hear from you. Email us to chris@thenakedscientists.com or tweet @nakedscientists if you want to get in touch via that route. Now, we have a very special extra guest who's with us this week, and that's Dr. Matt Mountain. He's the director of the Space Telescope Science Institute, and he's been overseeing some of the groundbreaking work that's been done with the Hubble Space Telescope, as well as working on its successor, the James Webb Space Telescope. And he's with us to answer some of my questions, but also, more importantly, some of your questions this week, and to tell us a bit about the project. Hello, Matt.
Hello there, Chris.
First of all, can you tell us what is the James Webb Space Telescope? What will it do?
Well, the James Webb Space Telescope is designed to be the successor to the Hubble Space Telescope, if you like, sort of Hubble 2.0. It's designed to work not, as the Hubble is, at optical wavelengths, but actually at infrared wavelengths, and it's much bigger than the Hubble. It's 6 meters across, 6.5 meters across, when the Hubble is only 2.4 meters across. So it's a very big telescope, which actually has to unfold on its way to orbit, roughly 4 times away from the distance from the moon to us, roughly 1 million kilometers away. And it's designed to look at the very first galaxies that ever formed in the universe's history, and we hope look at planets that are orbiting other stars and actually perhaps detect for the first time liquid water on those planets.
How was it conceived, and how is it being constructed, and how far along are you?
It was conceived by people at the Space Telescope Science Institute and the astronomical community in the US generally, and now in Europe. As the Hubble started work, we began to understand what the limits of what we would be able to see with the Hubble. For example, we began to understand there was actually a whole class of galaxies, very early galaxies, that the Hubble could only barely see the sort of peaks of the iceberg, and there was the whole sort of hidden universe in the infrared hidden, which in fact we call the Dark Ages. It's the time from when the Big Bang and the background radiation and the sort of the irregularities in that radiation turned into galaxies, and then galaxies appeared, and the galaxies we see in the optical come from a certain point back in the Big Bang, roughly 13 billion years ago, but we know the Big Bang started 13.7 billion years earlier, and that period in between, this Dark Ages, was inaccessible, and we realized there was a very rich universe there, and we needed a telescope that was much bigger than the Hubble, that could operate in the infrared. And so it's been under construction for over 5 to 6 years now, and each of its mirrors are in a as part of a hexagonal segment. It's rather like a ground-based Keck telescope, which is a very large telescope in Mauna Kea in Hawaii. And this telescope is made of segmented mirrors that all have to operate as a single mirror. And so it's a very radical design, and it will fly far beyond the moon at a point called Lagrange point 2, which is a sort of stable point beyond the moon, where it will cool down to a ridiculously low temperature, roughly 40 degrees Kelvin, which, I'm speaking from the US, is roughly minus 400 degrees Fahrenheit. So it's going to be very, very cold. And where we are right now is all the mirrors have been made. In fact, last week they were all completed. We have had some problems with cost overruns and some of the technical problems. We had to invent 10 new technologies to get this telescope going. But we're hoping to get this thing launched by 2018.
Yes, that's a bit of a sore point, though, isn't it? Because, I mean, if you look at the history of the James Webb Space Telescope, it was conceived in, the mid-90s. It was supposed to be flying by the mid-noughties. It was supposed to have a price tag of $500 million. That price tag is nearly $9 billion. So how optimistic are you that you will be seeing this thing returning data to Earth by that date?
Well, it was never actually supposed to. You're absolutely right. There's a lot of controversy going on right now. But it turns out that it was never supposed to be flown for $500 million. I mean, that was an estimate that people thought you perhaps could actually get something like this going if you launched it by sort of the late 90s. And by the time people started studying this, they realized that really something of this scale was going to cost between $3 to $4 billion if we could get it launched by sort of 2011. But delays and some of the technology challenges really have pushed the whole launch date out. And as you push the launch date out of these very, very complicated telescopes, the costs go up. And on top of that, we then started actually realizing we need far more complicated instruments than had originally been put together. And you stack all that up, and yes, you're looking at a price tag probably to get this thing launched of at least $8 billion, which of course is an enormous amount of money. But the Hubble itself, to get it launched in today's dollars, cost roughly $10 billion. And so for something of the order of the cost to get the Hubble launched, you're getting a telescope which is almost 4 times larger and incredibly more powerful and in a much more stable orbit than where the Hubble is.
And I mean, just one of the first things you said was this thing has got to unfold. That immediately sort of rings alarm bells that from a telescope you're trying to position your mirrors to within a wavelength of light, I guess, a really good quality telescope. That's got to be a serious challenge.
Oh, absolutely. And in fact, when you first watch the movie, and you can go to one of our websites and you can watch this thing unfolding, people do actually turn to you and say, "Are you kidding?" What they've forgotten, of course, is on the ground. For example, the 10-meter Keck telescope on Mauna Kea, it has lots of segmented mirrors, and it holds its figure perfectly in wind at all conditions on Mauna Kea, because what we use is a thing called a wavefront sensor, where we actually measure a star from the mirrors, and we measure the wavefront and then correct, because each of these mirrors has an individual adjustment on it. So we're constantly adjusting these mirrors to actually have them line up as a perfect single mirror. And that technology was, in fact, mastered back in the 80s by the Keck telescope on the ground.
Matt, let's take a look at some of the questions that people are sending in. If you'd like to submit a question for Dr. Matt Mountain to answer about his work in relation to imaging in space and what these kind of telescopes can do and will do, you can email chris@thenakedscientist.com or tweet @nakedscientist. I've got one here from Pekka Oelinki, who's got on our Facebook page. Matt, he says, would the new telescope be able to see the moon lander or some other man-made debris on the moon?
Unfortunately not, but not because it wouldn't have the resolution. As I said before, this is a very cold telescope, and so it sits at this point Lagrange 2, which is roughly 4 times the distance of the moon, and the moon is a very warm object for an infrared telescope. So in fact, we've designed this big sunshade, which is the size of a tennis court, precisely to block out the heat of the sun, the Earth, and the moon. So we can never look back at the Earth, the moon, and certainly not the sun. And so unfortunately, the moon will remain inaccessible to us.
This one here from Nish Nayar, which is sort of related to the resolution, because obviously resolution is important, and we've sort of touched on this. What is the resolution or quality of the images that such telescopes like the James Webb can capture, and how much computer memory is this going to take?
Well, the telescope is in fact bigger than the Hubble Space Telescope. It's 6.5 meters, but it's designed to image in the infrared. And its images in the infrared will be as precise and as fine as the Hubble images are at the optical. So it will take as spectacular images as the Hubble does at infrared wavelengths. And so for the first time, we'll see the universe in the infrared with the clarity and the spectacular image quality of the Hubble Space Telescope. The sort of size of the cameras are actually very large. We've used the latest infrared array technology. And one of our prime cameras, called the near-infrared camera, not very imaginative, I'm afraid, will actually take instantaneous pictures which are roughly 33 megapixels in size. So it'll be very large images.
And this is a very poignant question from Jeremy Baker, who says, what will NASA do with the equipment that's already been made if Congress cuts the program? Because obviously they're looking to make savings, and there is a danger that the James Webb might not progress on the grounds of there's no money available.
It is certainly one of the worries. I mean, the greatest tragedy here is that the mirrors, which are the most complicated part of the telescope, are in fact completed. And so we now have, at the Goddard Space Flight Center here, roughly 30 miles south of here, all 18 mirrors, each one as precise as the Hubble Space Telescope, in boxes waiting to actually be assembled into a telescope. And the instruments, many of which were built in Europe, and in fact the majority of the instruments actually come from European nations, and the UK, for example, is producing something called the mid-infrared imager, and it will be arriving here soon. So we will have these instruments also ready to go. And it's precisely because we have got so far with this that there's a lot of rethinking going on about whether this was the right decision to take it was the House. In the U.S. system, there's the House and the Senate that's decided on funding. The House first voted to actually not fund the James Webb Telescope. The Senate has yet to speak on the issue. And I think people are beginning to scratch their heads and think, hold on a minute, we've got all this hardware. Is this the right moment to actually stop the funding?
Let's hope not. Thanks for joining us, Matt. You stay there because we've got lots and lots of questions to put to you. You're listening to The Naked Scientists with Chris Smith, Dave Ansell and Emma Stoy. We're answering your science questions for you this week. And if you would like to join in and ask us something, or Dr. Matt Mountain, our guest this week, email chris@thenakedscientist.com. You can also tweet @nakedscientists if that floats your boat.
Bringing the facts to bear. The Naked Scientists.
It's The Naked Scientists with Chris Smith, Dave Ansell and with Emma Stoy. And Maridel's got a spacey question for Matt. Hello, Maridel.
Hi.
What would you like to ask us?
So I was wondering what determines the rate at which a planet or satellite rotates about its axis, and I was wondering whether these rates have changed over time. And in particular, is it just a coincidence that our own moon rotates about its axis at the same rate that it revolves around the Earth?
Over to you, Matt.
Well, that's a very good question. And it's actually, the interesting part about this is how do you actually stop a planet from rotating? Because the way planets are actually formed, the only way planets can be formed is in very large spinning disks. As the early young stars collapse, they begin to actually have to lose angular momentum. And so the dust clouds themselves are sort of naturally spinning. It's much easier to make things spin than it is actually to have things stationary. So as the planet system forms, the disk spins faster and faster to lose the angular momentum, so the material can then fall towards the star. And out of this collapsing disk, you get these sort of lumps and bits and pieces which become planets, which are intrinsically spinning from the angular momentum of the overall formation disk. Then, as the planets evolve and as they begin to clear gaps and so forth, they bump into other things which begin to either slow them down or in some cases even spin them up. And it becomes a very complicated interaction. Sort of if you spin a whole bunch of marbles in a bucket or something and just let them go, they'll all start bumping into each other. That's essentially what happens in the early planetary systems. And at the end of all this process, they basically, as more and more material gets swept away and the planets become more and more isolated, they're basically left with whatever spin they last had at their last interaction, whether it be the intrinsic angular momentum of the disk or angular momentum that they actually gained or lost as they bumped and smashed into each other. The case of the moon is actually very interesting because this is what's called tide locking. In the case of the moon, you can get to a certain point where if you're spinning at a certain rate, the angular momentum of the Earth and the moon begin to interact, and they can actually lock if they're at the right distance and going roughly at the right speed. And this is, in fact, what happened with the moon. It became tide-locked with the Earth and is now, of course, rotating in this locked sense that you only ever see one face of the moon at any one time. The only thing that will now change the rate of the moon over shortly if something hits it. Now, it will actually all begin to slow down because it's all moving slightly. It's losing angular momentum because of the tides on the Earth are actually putting a little bit of drag on the moon's rate. So over billions and billions of years, things may go out of lock again. So things do change, but it can take a very long time. In the very early solar system, these things were happening very, very fast.
Matt, brilliant answer. Thank you very, very much. Let's just quickly answer this question for Norman in Hunstanton, who says, is the medication oxytetracycline related to the tetracycline you were discussing? The answer is yes. They're all families, they're all molecules which are structurally related to each other. And Alan in Orpington's on the phone. Hello, Alan.
Hi there.
Go ahead.
My question is about the rubber that is lost from the surface of tyres throughout the world. All the time, every country, 24 hours a day, are losing minute amounts of rubber and wearing their tyres out. Where does it all go? Does it turn into a dust? Does it mix in with our water systems? Or is there a great big well at the bottom of the sea where it's gathering? Where does it go to and what does it do?
Certainly if you've ever changed a bicycle tyre, you'll know where quite a lot of it ends up, and that's all over your hands because you get covered in a horrible black gunge, which I think is mostly tyre rubber. Then what's going to happen to a kind of black powder all over the road? It's going to get caught up by water and washed away. I imagine rubber is a natural thing, so eventually some of that could be broken down, I'd have thought,
biologically. It's vulcanised though, isn't it? Because it's got sulphur added, so it cross-links it very, very hard to make a material break down that's been modified that way. I think it is quite persistent.
So eventually, but that's going to be a very, very, very slow process. So I would have thought most of it ends up in sediments in sort of streams and rivers, and it will slowly get fossilised in there or at the bottom of the sea, and it will sit there until it's degraded and turned maybe back into oil.
It turns into millions of tonnes of rubber on the roads every year, actually. I calculated how many tonnes of rubber we get through in the Western world every year. Just some simple back-of-the-envelope calculations. Millions of tonnes of rubber get used every year, and as those tyres are being replaced, you can therefore work out that it is millions of tonnes of rubber that are worn out on the road surface. So there you go. Emma.
So now, one of the most promising technologies for tackling rising carbon dioxide levels in the atmosphere is known as carbon capture and storage. The idea is to trap carbon dioxide from power stations inside rocks rather than release it into the atmosphere. But what if, instead of just storing the carbon, you could instead turn it into something useful, like bricks? Planet Earth podcast presenter Richard Hollingham reports from the University of Nottingham for us this week on a new technique dubbed carbon capture and utilisation.
They look like large boiled sweets, or perhaps something you'd use to make gravy. But when you bang them together, they're as hard as bricks. Anthony Benham is Business Development Manager at the National Centre for Carbon Capture and Storage.
One of the experiments that we're trying to do here is to react carbon dioxide with naturally occurring minerals. In this reaction process, you actually produce a new type of mineral that can effectively be used in the construction industry, for example, producing aggregates, things like that.
This process of combining carbon dioxide with rock turns out to be nothing new.
What we're trying to do is accelerate the natural process of weathering that occurs in the environment. So certain types of rocks react with the carbon dioxide that naturally occurs in the air and produce new minerals. This occurs in the normal everyday environment. Is a very, very slow process. So what we're trying to do is accelerate that process, and in doing so you produce these effectively oxo-cubes of different sort of minerals, if you like. So this one's quite a sort of a brown colour, and we've got this one here which is almost pure white, looks a bit like chalk.
So you bump them together. The white one's quite soft, this brownish tan coloured one, the both of which fit in the palm of your hand, that one's quite hard, so you can make different things out of them.
Yeah, that's right, and the products that you get will essentially depend on the materials that you use at the start of the reaction. For example, we use a lot of silicate minerals here, magnesium silicates and calcium silicate minerals, and depending on the quantities that you use will partly determine on the end products and therefore the colour that you get at the end of the reaction.
So we close the cylinder over there.
The reaction itself takes place in a sealed metal flask with a mixing paddle. It looks a bit like an industrial kitchen mixer.
We tied the screws.
In the lab, researcher Marco Dree talked me through the process, which even sounds like it could be a recipe.
We just mix our feedstock and with the CO2. So we mix them together and we produce our final product, which is the mineral carbonate.
But at the moment, that final product isn't very big. Even though each domino-sized tablet contains 3 litres of carbon dioxide, you'd still need a lot of these tablets to make even a single house brick, let alone a house. Mercedes Morotto Valla is the Chief Scientific Officer for the National Centre.
Yes, you are absolutely right. We need quite a few of these to actually build a house. These are just demo pieces that we built because they are easy for us to take around and they are easy for people to think about this as something that the CO2 has been solidified and now they can walk out of the room with this on their hands or in the pockets. But you are right that we need to scale up the process, and we are currently involved in a series of projects looking at the scaling up. So actually we can see the potential and the feasibility of this technology in the UK.
And how would this work in practice, would you have a brick plant next to a power station, or how would this work in practice if it did work?
Yes, I mean that's one of the things that we are now involved in a project together with the Energy Technologies Institute, Caterpillar, and also Shell. And what we are looking is at the feasibility of this technology in the UK. So we'll be able to see in which cases or in which locations it makes sense to build plants that will actually take the CO2 and mineralise it.
One of the other considerations is that the process itself uses energy, which rather defeats the object if making the bricks involves generating more carbon dioxide. Anthony Benham.
We're looking at ways of accelerating the reaction using typical atmospheric pressures and temperatures and varying the conditions and the concentration of carbon dioxide that you use and the quantity of material that you use in the reaction, because ultimately if we are to produce this at a large scale, then you want this to be using the lowest amount of energy that you can.
So if they succeed in scaling up this technology, future power stations could be built with bricks using emissions from power stations.
Planet Earth podcast presenter Richard Hollingham reporting from the University of Nottingham. And you can hear the latest Planet Earth podcast by visiting the Naked Scientist website. That's at nakedscientist.com/Planet Earth. Dave, JR has got in touch and says, if you're in space and you throw liquid into space, does it become a solid or a gas, or does it stay just the same?
It fundamentally depends on the liquid and where you are in space. If you throw water out into space about where we are in the solar system, what's going to happen is all of a sudden it's going to be any water that evaporates off it isn't going to come back again. It's a hard vacuum, so it's going to boil away, and as it does that, it's going to get colder. At some point it might freeze, but eventually then it will still sublime, and eventually it's going to all turn into a gas. If you did the same thing where it's very, very, very cold out near Neptune or something, then it would be so cold it would just freeze. You'd get a bit of evaporation, it will cool down and freeze, and it will essentially stay there as a lump of ice. If you use different liquids, different things will happen. Things like ionic liquids, they boil away so slowly that you could just have a blob of them which sat around
As a liquid
permanently.
And what about on the International Space Station? If an astronaut sort of had one of those burps that occasionally has a little bit of follow-through, for example, or just squeezed his packet drink a bit hard, what would you see?
So if it's not going to evaporate, then the major force affecting it is surface tension, the only force which is left. So essentially you get a huge droplet of water which is kind of held together by surface tension that will bobble around and just sit there floating in space until you either drink it or it hits something.
Distilling the best science. The Naked Scientists.
And this is The Naked Scientists, Chris Smith, Dave Ansell and Emma Stoy. Emma.
Now, a question for you, Chris, I think. Craig Lawrence wants to know, what are pins and needles and are they damaging?
Well, pins and needles occur when there's too little blood flow to a nerve or when a nerve has been damaged. The fancy name for pins and needles is paresthesiae. And what's actually happening is if you don't have enough blood flow to a nerve or you squeeze a nerve, and when you squeeze a nerve, what happens is that the blood which is supplying the nerve comes from tiny blood vessels in the wall of the nerve, so the pressure closes those vessels off. Nerves have an extremely high metabolic rate. They consume energy faster than almost any other tissue in the body. So if they don't have a regular blood supply, then they cannot keep themselves charged up, in other words, active. So they start to deactivate. And the first fibres to deactivate are the ones that are the smallest, and those ones are the ones that subserve pain. So that's why you feel these little jagged pinprick type sensations, because the nerves stop firing normally and they start to either discharge spontaneously, or the cells in the spinal cord that respond to them just start to fire off spontaneous nerve impulses because they can't hear the signal coming in from the nerve that's been squashed or deprived of its blood flow, and that's why you get the pins and needles. As long as you move your arm quickly or your leg or whatever body part to restore the circulation to it, it goes away very, very fast. It can be a big problem in people who fall asleep on a Friday night with their arm over the back of a chair, and this is called Friday night palsy, because in those individuals they actually squash the nerve in the arm and the blood vessels there, and as a result the nerve actually never recovers, and they can end up with this Friday night palsy, as it's called, and you get a limp arm that dangles there, not terribly helpfully. Right, Dave, you've got to help stop a fight. Quite literally. Michael Cartman has got in touch and he said, can you help to settle a dispute between friends who fancy ourselves as science geeks, but we really are in way over our heads? We both agree that a black object will absorb thermal radiation more readily than a white object. The dispute, though, is whether the reverse process occurs. Does a black object emit thermal radiation more readily than a white object? Thank you very much, a fan across the pond.
Okay, to really understand what's going on here, you want to understand how light is emitted and absorbed. Essentially, when light is emitted, a photon of light, a little particle of light comes in, hits an electron, that gives it some energy, so it increases its energy. Now, that, depending on whether it's absorbed or not, will depend on the structure of electrons. If there's somewhere for the electron to go, if it can increase that energy and it's happy up there, then it will absorb the light. If not, then the light can't be absorbed, it will carry straight on. So if it absorbs, it's black. If it doesn't, it's white. And that means also that if you heat it up, if there's somewhere for the electron to go up to and it's black, then there's also somewhere for the electron to drop down, so it will also emit. So if something is good at absorbing light, it's also good at emitting it. So the black thing should be much better at emitting light than the white thing.
So if you have solar panels on your roof, for example, that are heating water, you don't want the water going through them when it's colder outside than the water is, because you're turning them into very effective giant radiators.
That's right, and if you want to cool down a spaceship, the only way of doing it is by radiation of infrared light. So you paint the outside of your spaceship, or the bits of the radiators really dark black, which is a much better emitting the light, and it's a much better radiator.
All right, slight twist to this story. If you're a cricketer and you're at Lord's, assuming it is sunny on the occasion you're there, not like we've been having lately, they wear white, ostensibly to reflect the heat back off. Would they be better off wearing black then, assuming they're going to get hot anyway? They can radiate the light and the heat better with a black surface.
They're very, very unlikely to be hot enough to be radiating more heat than the sun is putting down on them, because the sun has got a kilowatt per square metre, and you're going to have to be very, very warm before you're emitting that much heat. So I think you're still better off being white.
Brilliant stuff, Dave. Now, Emma, this one I think is for you. David has sent this in specially for you. Here it comes.
Hi there, Dr. Chris. My question is this. What's the zoological term for animals that defecate indiscriminately anywhere, anytime, like horses, deer, rodents, and animals in which there's some component of volition, like cats, dogs, and humans? Is there an evolutionary advantage of one style over the other? My guess is, if you have to stop what you're doing every time you want to take a do, it makes you kind of a squatting duck for predators. Anyway, aren't we fortunate that we fall into the group of mammals that get to decide where and when we want to do our business? Can you imagine? Schools, supermarkets, hospital corridors, even houses of worship with human dogs' eggs all over the floor. Can you imagine how awkward human basic interaction would be? Dating? And it would be totally disgusting. If an alien species ever visited our planet, they would be sickened by our behavior. They would be justified in wiping us out, too. We wouldn't even be fit to keep as pets. I guess we just lucked out. Anyway, I'm sure you'll know the answer to this one. You always do.
I guess he's never been to Glastonbury, has he? Emma, what's the answer?
And appropriately, the answer is actually rather messy, if you'll forgive the pun, because there isn't a definitive answer, and I don't know if there's a zoological term for animals that just go whenever, wherever, versus those who can hold it. I think it's just termed sort of bowel control or lack of bowel control. So whether an animal goes everywhere or they go and off to do it somewhere specific depends kind of on the nature of the poo itself, which might be dependent on the food that the animal eats. So it tends to be that sort of very non-toxic vegetarian poo, which is no harm to the animal at all, can be done wherever, and there's no danger of the animal being around that poo. So you'll definitely notice if you have rabbits or guinea pigs, they just poo all over the place. In fact, guinea pigs even eat their poo, which is really disgusting to us, but great for the guinea pig because it gets an extra meal. Whereas animals with more sort of nasty parasite-laden poo tend to go off and poo somewhere else. So horses in a field, they tend to poo in clumps, and they never feed around that clump, so the grass gets really long, because they can have some really nasty kind of worms and parasites that get inside them if they ingest anything which lives in their poo. Birds as well, you'll notice they always poo there'll be clumps of poo below the bird's nest, but they don't tend to poo in their nest. In fact, some birds actually remove poo out of their nest and carry it off and drop it somewhere else. And that's thought to do with the parasite burden. Another dimension to this is actually communication. Now, you'll know that many animals communicate using smell. So it's known that big cats, such as cheetah or lions out in the savannah, tend to poo out in the open deliberately to mark their territory. In fact, that's often how they're tracked. And hippos use their tail to actually swirl poo around in the water where they go, again, to mark their territory. And as you mentioned in the question, being caught as a sitting duck and not wanting to be caught by predators, that could also have something to do with it. So again, horses and animals such as deer can definitely poo while they're actually running along. So I should have thought that's useful. I hope that answers the question.
I guess also there's a big difference between herbivores and carnivores, in that herbivores have got to eat a huge amount more food, which means there's a lot more to go out the other end. And also carnivores, if they're eating meat, then the kind of bacteria which are going to be going in their guts on that meat are also more likely to be close to the ones which would eat them meat, which are made out of meat as well.
Yeah, that's definitely another point to make.
Terrific. I've got one here from Ron Murphy. He emailed us to say neurons don't divide, but new neurons are created from stem cells. So how do these new neurons come to be used in the brain? I presume they don't migrate, but they instead extend their dendrites and axons. But aren't the neuron bodies still building up into specific sites of generation? Excellent question, Ron. The answer is that scientists discovered, much to their surprise, about 15 years ago, that contrary to prevailing wisdom, nerve cells in the central nervous system, in other words the brain and spinal cord, are actively dividing into adult life. We previously thought that once you go beyond the early years of life, maybe 1 or 2, no more nerve cells are born in the brain. But some studies done on cancer patients who were taking drugs that labelled up dividing cells led people to realise that new nerve cells were being produced into adulthood in certain sites in the nervous system. One of them is in the hippocampus. And what happens is that there are cells in a specific region of the hippocampus, the site in both sides of the brain concerned with learning and memory. And coming out of this specific site, the subcortical plate, there is a population of stem cells there which bud off and they produce one new neuron and one new stem cell. And those new neurons, then, they do migrate. They use glia, which are supporting cells in the brain, almost like tight ropes. And they walk along these tight ropes, crawling along them to a site where they want to end up. And after that, their fate is one of two things. One, they can survive. The other is that they die off, and a proportion die and a proportion do survive, and we think they're very important for learning and memory and also maintaining healthy psyche. Because if you look at how antidepressants work, people thought they were just working via increasing the levels of certain nerve transmitter chemicals. Turns out that's not the whole story, because what they've now discovered is that these nerve cells can be made to survive in much greater proportions if you take antidepressants. So they think that one of the reasons why people who are on antidepressants get better from their depression, and it takes several weeks for the depressive symptoms to go away, despite the fact that you can register a change in the nerve transmitter chemicals almost immediately, is because it's taking a while for new nerve cells to accumulate in the brain, and then they work a bit like a neurological sticking plaster. They plaster over the damage, and they help to wire themselves in, integrate, and restore more normal neurochemistry in the brain. So I hope that answers the question. Basically, you do give birth to new neurons. They do migrate to certain restricted targets in the nervous system of adults, and that goes on right till the day you die. Right, now it's experimental time. Dave is wielding a laser.
This is a lovely experiment I saw at a conference recently. Basically, what we're going to do is get a droplet of slightly dirty water, somewhere organic. This water's out of Ben's water butt.
Out of the toilet for a minute.
Yeah, I guess that would work, although I'm not going to recommend it. Although what I've found works really, really well is if you water a plant, throw over water a plant and suck up some water which has just kind of gone around the side of that.
Trickling out the bottom of the pot, just suck some of that up.
Yeah, that's the idea. Now, you want to get a drop hanging. You could do that with a piece of string or some kind of fork or something, just get it hanging there. But it's a lot easier to use a syringe, and I have one hanging around, so I'm going to use that. So I'm going to suck some water up into the syringe.
So Dave is now drawing up from a pot of rather grotty-looking water, a syringe full of said water.
And I'm just going to hold it in a clamp. Doesn't really matter how you hold it up there. You just want to be able to get it there so the drop hangs down. I'm just going to squeeze it down and get a drop so it's almost falling off. Oh, that one did fall off. Try another one. Just get it down so it's just almost falling off and it's just sitting there.
Now, we should point out at this stage, so Dave has the syringe in a retort stand, hanging there with a tiny drop of the water hanging off the bottom of the syringe. And what's this box with a piece of paper sort of stuck onto the front of it, which is about 6 inches from that syringe?
Okay, that's coming to the next stage, which we need a laser for. You use a laser so in order to be able to see things. I'm going to turn the lights off, so I'll just go over and do that quickly.
And it has gone very dark.
So now it's much darker, and we should be able to see things a lot better. I'm going to take my laser, and I'm basically just going to shine it through the drop. So what I'm doing is shining it through the drop.
We've got some light appearing on the screen, on the white piece of paper stuck to the box. And, oh well.
Oh wow, there's sort of things moving around there. Are they bacteria?
I mean, it's very, very hard to tell because they're not a very clean picture, but you can certainly see objects moving around. Some of them look completely dark and black, which are probably opaque. So those are actually just probably just plain shadows of a little bit of dust or a little bit of dirt in there. Some of them are sort of round, slightly dark circles in the middle, surrounded by lighter stuff around the outside. So the reason why this works at all is because of a special property of laser light. Laser light is very, very parallel. So it's as if it was coming from somewhere a huge distance away. So all the light rays are almost exactly parallel, which means that if you create a shadow with it, that shadow is incredibly stable. If you create a shadow, if you just put your hand out in front of a normal light, that shadow kind of goes fuzzy around the edges very quickly. The shadows from a laser don't. This means that you can create very, very tiny shadows from these little tiny objects, little creatures and little bits of dust inside the water droplet. And then when the light hits the end of the water droplet, it gets focused down into a point. And then once it's gone through that focus, it spreads out again. So as the light spreads out, the shadows spread out and they get magnified a couple of hundred times.
So effectively you're using the water droplet both to provide you with your study subject, but also as a lens, as a focusing system.
It's not acting like a normal lens, but it is spreading that light out. So you're taking small shadows and turning them into big shadows, which you can actually see.
And then what you see projected onto this piece of A4 paper screen 6 inches away is an area, I don't know, it's a spot of green light that's a bit more diffuse, probably about 5 or 6 centimetres across a circle, and superimposed on that we're seeing these black, they're nearly black, they're sort of shadows bobbing around on there.
There's actually a couple of types. Some of them are almost black, which probably are just plain shadows. Other of them are kind of they're sort of circles, dark circles with a bit of white in the middle and white rings around the outside. I think those are probably cells, so bacteria or something like that. And a cell has got some sugar inside there, which slows the light down a bit. So they act as incredibly weak lenses. So the light comes to focus slightly earlier with those, which means that you end up with a kind of dark ring in the middle, and then that focus light spread out. So it's brighter out, slightly just around the edge, and darker in the middle. And then they bimble around. Some of them are actually active, especially the ones I had that was playing around. There's some beautiful ones on the video I've put on the Kitchen Science part of the website.
You're using a green laser pointer to do this. Will any kind of laser or any coloured laser pointer work?
Basically any laser, anything with very, very parallel light. I mean, in theory, you could do it from a very, very distant, very, very small light source, but they don't really exist bright enough to be able to project nicely like this.
We're going to have to leave it there, but if you want to see a video of this working, you go to our website, nakedscientist.com/kitchenscience, and Dave has put a video and a write-up of how this works, so you can try and have a go at doing this at home. But talking of tough nuts to crack and tough questions, here is a very smelly wet one with Diana.
This week, I'm glad it's not raining.
Hi, I'm David from London. I wondered if you could tell me, why do wet dogs smell?
So what is it that sparks that familiar soggy doggy stench?
Hello, my name's Dr. David Williams. I'm a vet at the veterinary school. I generally deal with animals' eyes and their eye problems rather than their smelly skin problems, but I'm always on for doing a bit of research into interesting questions. And this is an excellent question. It's one that really doesn't seem to have been asked or answered, as far as I can see, by scientists at least. But first of all, what actually makes something smell? Molecules have to leave the smelly object and get to your nose through the air. And that means that these molecules must be very small and volatile. That's to say, they must be easily evaporated. The chemicals that make dogs smell are mostly what we call volatile organic acids, and they're produced by bacteria from the fats that are breaking down from sweat. And that's maybe why we find these body odours unpleasant. They signal the presence of bacteria and decay and death to us. Their skin mostly has staphylococcal bacteria, which don't produce much in the way of smell at all. But they've got some yeasts too, which are really pongy. But why does the smell seem worse when the dog's wet? Here I think we have to go to some physics. The amount of evaporation of a substance relates to the concentration of the compound on the surface it's evaporating from and the amount of compound that's in the air just above the surface. So how might that change when it's wet? Well, if the organic acids are dissolved in water on the fur of a wet dog, as the water evaporates, the concentration of those smelly acids increases, so they'll evaporate more. So there are more molecules in the air for us to smell.
A bit of evaporation can effectively amplify the amount of volatile chemicals that emanate from a dog's skin, and Dr. Williams thinks it's the same effect that occurs when that damp earth smell is produced after rain. On the forum, both Air Thumbs and Dowsett hypothesised a very similar answer. And interestingly, it may alter the way dogs interact with each other when they're wet. So if you have a dog, watch to see if it sniffs differently at other dogs on a dry day versus a wet one. And from aromatic mastiffs to crafty calculators.
Hello, my name is Alison Mayshow and I live in London. And I was wondering, how does a calculator work? How can it make complex calculations in nanoseconds? Also, how does it display the result on the screen?
What mysterious workings are going on inside that plastic shell? Answers to Chris at thenakedscientist.com. You can Facebook us, you can Twitter at Naked Scientists, or you can write on the forum, which can be found at thenakedscientist.com/forum.
Diana O'Carroll with this week's question of the week. Well, that's it for this week. Just time to acknowledge Jen in Cambridge, who said, is the shadow that Dave was seeing in his experiment the same that you see from floaters in your eye? Dave thinks the answer is probably yes. Well, that's all we have time for. Thank you to our guests, Paul Forsyth from McMaster and Matt Mountain from the Space Telescope Science Institute, and our wonderful production team, Ben Valsler, Tom Simpkins, Miracenthalingam, and also our co-presenter this week, Emma Stoy. Next week, we're looking at the science of supercomputers. We'll find out how they work and the sorts of science that you can do with them, and also hear how distributed computing means that you don't need a supercomputer to do supercomputing at all. Send us your questions in relation to that to Chris at thenakedscientist.com. Have a great week and see you next time.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council, and UK FAST. For more information, look us up online at thenakedscientists.com.